I'm going to be talking through this paper called Show Your Work, Scratchpads for Intermediate Computation with Language Models out of MIT and Google Research. So that this paper sort of falls in a broader world of literature around evaluating actual code and code output, things of that nature. And this has been an evolving field, one that has historically had pretty poor accuracy and performance of models because it is a understandably pretty difficult problem. So what the authors are providing here is a solution to that problem, namely the use of a Scratchpad. So what is a Scratchpad? You can think of the Scratchpad similar to a code trace. So the idea here is we're not just going to output what does the code evaluate to, but instead we're going to say, okay, what does the code evaluate to, but in addition to that, as like sort of appending to that output in the beginning, specify some of the intermediate output and various steps that we sort of take along the way to get to that answer, which I think in the context of a transformer makes sense. They talk about some of the philosophy behind this. So yeah, they are modifying the task design, right? And they're going to allow the model to produce an arbitrary sequence of intermediate tokens, which they call Scratchpad, before producing the final answer. We encode the intermediate steps of the algorithm as text and use standard supervised training. They talk a little bit more. So the two problems that they're really looking at are neural algorithm induction. So learn an algorithm, and each training example gives a single input and desired output. So that format there. And then they also cover learning to execute, which is where you actually learn to execute, right? So we want the model to produce the result of the program representing the source code on some input. So we want to solve these pieces, and they are specifically using a decoder-only transformer. So yeah, some of the ideas here: the model has adaptive computation time. It can now process the information for as long as needed, because it can build out a longer Scratchpad. Key caveat here is that it is as long as the actual embedding dimension of the transformer allowing for output, which is apparently 512 tokens, I believe. And then the model can store the intermediate state of its computation in the Scratch buffer and refer back to it by attending to its context. So I mean, this is sort of the bit where I'm like, okay, yeah, like that seems reasonable, right? So they also aim to reduce the propagation and compounding of small errors. They talk about this being a thing for neural Turing machines. So let's get to some output results. So this is what they show for a baseline and the Scratchpad. Just some like explanation here on like these three different graphs. So this is in distribution. This is out of distribution, these two here. More specifically, the task that they're training this piece on is addition, so something of this nature. And when they say 9 digits, they're just building out the addition to 9 digits or 10 digits, which is out of the distribution of what it was actually trained on. So these results are obviously promising, insofar as the Scratchpad looks better. However, what sort of strikes me as a little strange here is this lower accuracy in the beginning. It makes sense that like the baseline model, which doesn't use the Scratchpad buffer, is not performing well consistently, or goes up. But I'm sort of curious as to why the parameter count does like have this positive relationship with accuracy. So yeah, definitely curious to talk a little bit more about that. Beyond this, they also look at polynomial evaluation. So this is definitely a little bit of a harder problem. So the idea here is to produce this sort of output. So 7x squared plus 7x plus 5 at x equals 1. What does that output equal? So the idea then, you do your 7x, get your 5, so on and so forth, to get to 5 is the answer. So they basically are just sharing results at this point. So in this case, the Scratchpad pretty significantly improves performance. They also fine-tune this, so yeah, you can imagine that the fine-tuning case, you have a pre-trained model, and then you are like learning to execute with Scratchpad more specifically from that pre-trained model. So yeah, important to note the motivation behind having this in this experiment is that there was some other paper that showed that here, I forgot if it was GPT-3 or some other transformer model is capable of doing some direct prediction for polynomial problems specifically. So that is why they include that there. Let me see if there's anything else here. Oh yeah, so they talk a little bit more about the trace here. So they are specifically looking at the ordered sequence of source code lines executed and the state of the local variable after each line is executed. Oh, sorry, I'm getting a little ahead of myself. This is for the executing Python programs. So you can imagine how this works. Their language model is asked to predict the results of executing a given Python program on a particular input. So, like I said before, they want to get a trace of the program, which makes sense as like sort of Scratchpad output, right, to keep track of variables over time. So one, they're looking to keep track of the ordered sequence of source code lines executed, and two, the state of the local variables after each line is executed. Varying degrees to which they actually want to get this right. But you can imagine if you are getting this more or less right, it's more likely that you are going to get the final output execution prediction correct. So they have an example here, and they're able to show that with Scratchpad, they're able to pretty significantly improve on performance. So that obviously is pretty promising, right? But yeah, they look at some other models that, or some other data augmentation techniques that can further improve things as well. So let me just look through here really quick. Great. Okay. So yeah, the next piece that they're sharing is again on direct execution, but what they want to do is get a sense of perhaps other means by which they can improve performance. So looking at this table 3 here, they're looking at, so in this case, direct execution is represented here, Scratchpad is represented here. So MBPP is a particular data set for Python code execution. So the results that we really care about are comparing, say, this with this and this, sorry, and this with this. So just to give a broader overview of what they're doing here. So the baseline performance, the direct execution actually outperforms their model. But they do this data augmentation technique where they are generating additional Python programs based off of the programs in MPPP. And as you can see, that sort of swaps around the role here, but at least this per task execution accuracy, where yeah, we go from 5.1 to 17.3% accuracy, and this actually downgrades in the case of the direct execution. Similar stories for the, for example, execution accuracy as well. So that is promising. Further motivates the idea that maybe in addition to this task augmentation, they can just look at integrating other data sources as well. And fortunately, there are other data sources. So CodeNet is a repository of people's answers to the coding problems on some website where people solve coding problems. They're apparently both incorrect and correct like solutions to solving these problems. They train on all of them. I think that's sort of strange, but combining that and also combining a single line data set. The example that they gave of that was here. So just a bunch of Python single line coding output. I think that is interesting and makes sense as a training criterion, or sorry, a training data set to be using. Finding all these three clever dramatically improves Scratchpad accuracy. It would be cool if they decided to include direct execution as well for that particular data set. But yeah, obviously with the augmentation of MBPP, it sort of suggests that they did not perform well for direct execution. And that is the paper. Basically, in summary, looking at how to use the Scratchpad sort of inherent structural capacity of transformer models to produce these sort of extended outputs that I think have been sort of common in the literature, and applying it to code execution in a way that seems to improve things. But at the end of the day, we're still looking at 46% accuracy. So, yeah, would be curious to hear people's thoughts.